So the setup is we have some high-dimensional data set, and we want to know if the data satisfies some property. Then we're going to consider the data as coming from some probability distribution. Formally, we want to decide whether this probability distribution has a certain property or whether it's far from any distribution that has that property, because if it's close, we can't really tell. And we want to do so using as few samples from the data as possible, and with a computationally efficient algorithm. And often we can test whether a property holds using less samples than it would take to learn the probability distribution. Now, in one dimension, for discrete distributions, there are a lot of results that give tight bounds on the number of samples needed to test many properties. But most of these tests for arbitrary distributions require about square root the domain size number of samples. And if you have high-dimensional data, your domain size is going to be exponential in the number of dimensions, and so we need exponentially many samples if we're going to use this type of algorithms. So, of course, we have to take advantage of structure in the data. So, if our data is structured, typically we consider the case when we have local dependencies, when some coordinates which represent some feature related to some other things, and we can represent this using a graphical model. In particular, we're going to be considering Bayesian networks, where the data has some causal structure. And so what you'd have is a directed acyclic graph, where each node it represents a variable with coordinates in your high-dimensional data. And what the graph says is that, so basically, the distribution of a node is going to depend on the values its parents take. So here, x3. Formally, we have a node like, say, here, x3. If we can condition on all nodes except this node and its descendants, so these four, then the distribution of this node is going to be the same as the distribution if we conditioned on its parent alone. And so this is a 7-dimensional graph that has 7 nodes. And the other parameter we're interested in is the maximum degree, the maximum number of parents any node has. And the things we're interested in testing are identity. We have some hypothesis Bayesian net Q, which we know, and we want to know, do our samples come from this Bayesian network, or do they come from a Bayesian network that's far from it? Closest, we have 2 unknown Bayesian networks. All we know about these is what the maximum degree is. We want to test if so we have 2 sets of samples, and we want to test if they come from the same Bayesian network. That's closeness. More specifically for Bayesian networks, we might be interested in testing structure. We have a directed acyclic graph, and we want to know, do these samples come from a Bayesian network with this graph? Never mind what the probabilities are. Now, we're considering binary Bayesian networks. So we're considering Bayesian networks with discrete nodes, which kind of, without just loss of generality, we can assume that each node is 1 bit. It's a Bernoulli. And this would take, so rather than 2 to the n, the size of the domain, it's going to take n times 2 to the d over epsilon squared samples if we wanted to learn these. And we're interested in tests which, when we can test with fewer samples than it would take to learn the network. And the results are, if we know the structure, then we can test with about square root the domain size, square root the number of samples we need for learning, except for the epsilon dependence. And this is kind of the same square root we got for the discrete case. So for product distributions, the simplest case when there's no edges at all, the variables are actually independent. We have a sample optimal thing for identity and closeness. With the general case, we have to assume something, which is this balancedness condition. A Bayesian net is going to be balanced if all the conditional probabilities are constantly far from 0 or 1. And under that case, we can also test identity and closeness with the sample complexity. When we don't know the structure, we don't know the graph, then in general, we can't test with fewer samples than it requires to learn, even for testing uniformity. The uniform distribution is close to a Bayesian net with every graph. And this, for some reason, this makes this hard. But if we assume in addition to being balanced that we're non-degenerate, which means, broadly speaking, that we're far from any Bayesian network with a different structure, in detail we have to check nearly related nodes. So the structure of a Bayesian network is determined by a number of conditional independence conditions. And we have to show that related nodes that we'd expect not to be conditionally independent are far from it. And in that case, the structure is unambiguous, and we can get these testing algorithms to work. So I might try and briefly say how we might go about doing a test for identity of, say, a known structure. And the basic idea of coming up with tests is much the same as we would do for other properties for testing identity of discrete distributions or something else. So the way we do this is we'd first find an upper bound on the total variational distance in terms of the parameters, these conditional probabilities, and the probability of the differential configuration, which is some function of the conditional probabilities of the ancestors of the node. And then we come up with an even more complicated formula, which is this thing, which is an unbiased estimator for this upper bound. So we have something whose expectation will be 0 if the distribution we're looking samples from, which is P, is identical to this Q. And if it's epsilon far in total variational distance, this thing is going to be has expectation at least epsilon squared. And so if the variance is small, we can just check is W big, and that will give us our identity test. Now there's some complications here. The number of samples we need for each node, for each combination of the parents, depends on the unknown, depends on the known network, which is not the one which the samples come from. So if we don't see enough samples to even compute this with root n over epsilon squared with our target sample complexity, then we know we're far. But if we can compute this and it's big, then we know we're far, and if it's 0, we know we're close. In conclusion, we can test Bayesian networks for these properties with fewer samples than need for learning. This is kind of a new area for high-dimensional distributions, so the question is, can we do this for other high-dimensional distributions with other types of structure? Thank you.
Questions while the next speaker is setting up? Salil?
Is there hope of removing the balances conditioning, or are there lower bounds or hardest results in this case?
Yeah, no, we don't have any lower bounds for the bounce. So maybe we can remove that as we can for products. But maybe we might have the wrong statistic, because I think the statistic I gave there is not tight. The inequalities in that are not tight if you're not balanced. And that's the reason why our algorithm probably doesn't work.
Go ahead.
But there's no theoretical reason why you couldn't get something that did.
Yeah, I'll show you something. All right, so let's thank Alistair again.